The topic of this video is the hydration of ketones and aldehydes. Hydration of a ketone or an aldehyde is the addition of water across the pi bond of the carbonyl. This can occur both with ketones, where both of the R groups are carbons, or aldehydes, where one or both of the R groups are replaced with hydrogen. Both of these reactions are equilibria. The ketone equilibrium typically favors the ketone rather than the ketone hydrate. In other words, the equilibrium constant is significantly smaller than 1. Aldehydes, on the other hand, are significantly more reactive towards hydration, and the equilibrium constant in these cases depends on the exact structure of the aldehyde. Why is aldehyde hydration more favorable than ketone hydration? The reason is that aldehydes are more electrophilic. Aldehydes are more electrophilic than ketones due to the inductive effect. We can see why if we compare the structure of a ketone to the structure of an aldehyde. Remember that a ketone carbonyl carbon has 2 carbons attached to it, whereas an aldehyde carbonyl carbon can have 1 or no carbons attached to it, as we see in the case of formaldehyde. The oxygen of the carbonyl is electron withdrawing in all cases. The carbonyl carbon is partially positively charged due to the electronegativity of the oxygen. In the case of the ketone, the carbons that are attached to this carbonyl carbon can inductively donate electron density to help stabilize the partial positive charge. This helps to cancel out some of that partial positive charge, making the ketone less electrophilic. In the case of the aldehyde, it only has 1 carbon attached to the carbonyl carbon that can inductively donate electron density. Remember that a hydrogen has no electrons of its own, and therefore cannot donate any electrons through the inductive effect. Because the aldehyde has 1 less carbon attached to the partially positively charged carbonyl carbon, that carbon has a larger partial positive charge than a ketone and is therefore more electrophilic. Formaldehyde has no carbons attached to its carbonyl carbon, only hydrogens. Therefore, it has the largest partial positive charge on the carbonyl carbon. Formaldehyde is the most electrophilic of these compounds, and it favors hydrate formation in the equilibria above. The equilibrium constant for hydration of formaldehyde is 40, significantly larger than 1, meaning that the formaldehyde hydrate is very heavily favored in the equilibrium. Next, let's look at the mechanism for this transformation. Hydration is unusual in that it can be either acid or base catalyzed. First, let's look at the acid catalyzed mechanism. The acid catalyzed mechanism has a weaker nucleophile, water, and therefore requires a stronger electrophile, the protonated carbonyl. Now let's look at the mechanism. In the first step of this mechanism, just like in other acid catalyzed additions to carbonyls, protonation of the carbonyl occurs. This protonated carbonyl is a stronger electrophile and has resonance stabilization. In the next step, the nucleophile attacks the protonated carbonyl. This forms the tetrahedral intermediate. In the final step, another molecule of water deprotonates the charged tetrahedral intermediate to produce the hydrate product. Next, let's consider the base catalyzed reaction. Because the base catalyzed mechanism uses a stronger nucleophile, hydroxide ion, it doesn't require strengthening of the electrophile prior to attack of the nucleophile. The overall reaction is the same, however this is carried out with base instead of acid. In the first step of this mechanism, the base, the nucleophile, attacks the carbonyl carbon. forming the tetrahedral intermediate. In the final step of the reaction, the alkoxide ion is protonated by a molecule of water to produce the neutral hydrate product.